Okay, so just so you know, my source here is where I'm getting a lot of this stuff is from a website called Paul's Notes. And Paul is a professor at Lamar University, and he has a lot of really, really good stuff on his website. So I was just kind of reading through his stuff and making my own lessons based on them, but I like the order that he teaches Calc 3 in. So, and this is a brand new topic. If you were in my AB class last year, you saw yesterday's lesson already, but you've never seen this lesson. This is brand new. So we want to talk about how to graph or write an equation of a line in 3D. Okay? So first let me present the need why we would need to do this. Okay? So you know that a line like 4x minus 3y equals 0, right? Or you could say y equals 4/3 x, same thing. That's just a line, in regular xy axes, that's a line. But it is not a line if we're talking about 3D that day. So, if you were doing a 3D discussion with your teacher, let's say, and I said, okay, everybody graph y equals 4/3 x, that is actually not a line, okay? Because it's a line only if you're on the xy plane. It has a slope of 4/3. So imagine this is like your desk, this blue desk. Maybe you bought a blue desk at IKEA. They have interesting furniture. So you bought a blue desk at IKEA. You're graphing a line. It's the line y equals 4/3 x. But then you realize, oh, this is an R3. This is like a 3D thing. I was supposed to graph it in 3D. Well, your line is part of the answer, but it's not the full answer. Imagine going straight up from here, just one space or whatever, to z equals 1, and then plotting that line again. See? Or going up another space from there and plotting again. See, this isn't a line at all. This is a what? This equation of a plane, as it says right here. Yeah, and there's no reason why we can't go under the desk, right? If you go down one space from this line, you get this line, which is under the desk, So what happens is you actually form an entire sheet of points. Some of you aren't even paying attention. I don't know how you plan on doing Calc 3 without paying attention. You get this entire sheet of points, not a line. Your line is one of the lines in the plane. Okay? So what you thought was a line is actually one of many lines. Because z isn't specified, so there's lots and lots of them stacked up, right? Okay, there's technically no amount of space between them. So it's just a continuous sheet of points. Okay, so this presents a problem. How do you define a line, right? How do you write the equation of a line if you can't use y equals mx plus b? Well, one of the reasons you can't do it is because of this stacking effect. Or can't do it yet, I should say. It's this stacking up effect. And the other reason is slope doesn't have as much meaning now as it did. Like 4/3 means like change in y over change in x, but it doesn't tell us how things change in the z direction. So our goal, let me just tell you what our goal is today. Our goal is to write the equation of a true line that's pointing in any direction at all. So it might be this red line right here. It's a little bit hard for me to draw, but imagine this is your blue IKEA desk, okay? And your graph of this line pokes right through the desk right here. So it's sticking up out of the desk, maybe even at an angle sticking up out of the desk, like this ruler sticking out of my desk. That thing can be drawn. It can be, portions of it can be measured. Each point has its own coordinates. We should be able to write an equation for this thing. But it seems to be eluding us. So far, we don't seem to be able to do it. So we kind of have to rethink everything about lines now. It's the most basic shape we've ever drawn besides points. Now we have to kind of start over completely from scratch and define brand new ways of thinking. So one way is to use what's called a vector form of the equation of a line. Okay, so you can just fill in the blanks here as I go. Vector form. What is the vector form of the equation of a line? Well, it's this here, what I just showed you. Okay? It's what you have right here on the paper. So I'll highlight it, and its name. Okay, the name is vector form. The equation is R of t equals x naught, y naught, z naught vector plus t ABC vector. Okay, so I don't want this to be confusing. I'm going to explain it as, after I fill in this little paragraph, I'll explain in my own words kind of what it means. And I think it will make sense to you. Okay, so t is just any real number. So it's a scalar, it's a number. And R naught is the vector x naught, y naught, z naught, which is the position vector for any point known on the line. So any known point on the line might be the nice way to write it. Any known point on the line. Okay? And vector ABC is any vector which, when placed tail to head with position vector x naught, y naught, z naught, would lead us from the point x naught, y naught, z naught to any other point on the line, or all other points on the line, technically. Okay, so this can be kind of mysterious, but let me just kind of explain it in my own words now. So to do that, I need a kind of a separate sheet of paper. So okay. Hopefully I can draw this well enough for you to understand it. Okay, so there's a random point in space. Okay, let's plot it right here. So you can draw this anywhere you want. This is the point x naught, y naught, z naught. Okay? There's another point somewhere. Okay? That's on this line. Remember, it only takes 2 points to define a line, right? Okay, so there's another point over here, let's say. Okay, so this point on the right is sort of the variable point. Okay? It's kind of like when you're doing y equals mx plus b, right? When I write y equals mx plus b, the b is this fixed point right here, right? And then the m is sort of a slope that gets you from that point 0b to others, right? For example, if m is 3, right, then you know if you go right 1 and up 3, you'll find another point, right? So I guess we're saying this is very similar. We're in 3D now, but like in the world of 2D, you have one point and a slope, and you can find other points using one point and a slope. Maybe the better thing to write here is y equals, or no, y minus y naught equals m times x minus x naught. Maybe we can draw that picture instead. You have a random point, right, called x naught, y naught. You have another point over here called xy, you see. The relationship between these is that y minus y naught equals m times x minus x naught. Isn't that true? Okay, everybody's with me on that? Okay, so you're starting with one point, and you're doing kind of a vector to the next. Okay, so you're starting at the red point, and you're vectoring over to the blue one. Okay, now this vector here, if I make it really long, it will take me to points that are further out on the line. And if I make it really short, it will take me to points that are near the red one. And if I make it sort of negative, I can get the points on the other side of x naught, y naught. So I really can use this basic idea of starting with the red and projecting a vector outwards from the red towards other points. Whether I go close or far, or even backwards, I can map out the whole line by starting at the red and going forwards and backwards. Okay? So this point here is the point x, y, z. And it is unknown. It is unknown, let's say. Okay, so what's the relationship between these two in 3D? It's very simple, really. This vector here is called the position vector for the point x naught, y naught, z naught. So this is your x naught, y naught, z naught. Those would be three numbers, actually, that you would already know. This vector is the vector x, y, z. When the tail is at the origin, the name of the vector is the same as the coordinates, okay? So we call that a position vector. These are vectors with the brackets. Make sure you write those. These are points with their parentheses. But since the tail's with the origin, the name of the vector and the point that's at the head are the same. He's in an AP exam. Okay. Okay, is everybody with me so far? Okay. So, if you draw a third vector, this green one here, we know that this vector will be the vector x minus x naught, comma y minus y naught, comma z minus z naught. And that's the vector that connects the 2 points together. See? And that's our line, right? That's the line. The green thing is sort of at least part of the line that we seek to find. See? Does that make sense? You guys follow me so far? Okay. So when we go back to our lesson, I haven't explained everything, but I've given you kind of a basic idea of what we're trying to do. We're going to try to stretch that green real long, make it real short, make it go backwards, and as we do that, every time we draw a new green one, it'll have various lengths. And the little red point at the head, at the head arrow, end of that vector, will be a new point on the line. So if we make this really long, we get a point over here on the line. If we make it really short, we get a point over here on the line. If we make it go backwards, we get points on this side of the line. Okay, so the green is effectively our vector. Our line, I mean. So here's what this is saying. Here is the original point, x naught, y naught, z naught. Okay? Here is the vector, this vector ABC is that green one I had up a minute ago. Okay? And the t stretches it to various lengths. Okay? So the t can be any number, and that's our variable actually. So in a very real way, this is like b plus xm. That's what this is by analogy. This is like b plus xm. If you want to think of it that way. This is kind of, it's not the y-intercept, but it's sort of that point you knew. And then this is your x now. It's actually t. And then this is like your direction. This guy provides the right direction. So this is a very informal explanation, but you can think of it as b plus xm. Okay? So ABC's job is to direct us in the right direction. T's job is to stretch and shorten this green vector. And x naught, y naught, z naught has one job: stay where he's at and provide a reference point. Okay? That's the best I can do in 5 minutes explaining it. But it's not hard to use. Okay? So for our first example, imagine if you knew that a particular line contained the point 2, 4, 3 and the point 5, 7, 8. Right? Now you can plot these if you want to, but it isn't really necessary. X naught, y naught, z naught can be chosen to be either of these 2 points. So you can pick either of these to be your starting point. It doesn't really matter. So I'm going to go ahead and pick the first one just because it's the first one. 2, 4, 3. Or you could use the 5, 7, 8. But it's a position vector. And ABC will be basically 5 minus 2, comma 7 minus 4, comma 8 minus 3. When you subtract these 2 points like this, you get that little vector that connects the 2 points, or at least a vector that points in that way. So that gives us the numbers, what, 3, 3, 5, right? Okay, that guy, he is sort of our slope. The 3, 3, 5 is kind of like our slope. And so now we can just write our answer. It's very simple. 2, 4, 3 is our starting point, our reference. 3, 3, 5 provides the green vector. T stretches it to various lengths. Okay, so what you're looking at here is a description. This is kind of the hard part to understand. But if you're able to follow that example so far, basically that right there provides, watch close, all of these vectors, watch very closely, watch my pen, okay? This vector, this vector, this vector, this vector, this vector, this vector, this vector. This whole span of vectors here maps out all the little points on the line, all of them. So what you're looking at when you see a vector equation like this, r of something equals, you know, whatever, and there's the vectors on top, what's happening is these points are lining up, and they are all the endpoints of various vector arrows. All of these vectors here are r's, r vectors, radial vectors from the origin out to a random point on the line. But they're not totally random in space. It's organized according to x naught, y naught, z naught plus t, a, b, c. Okay? So you kind of are writing an infinite number of vectors at the same time. Okay, if you didn't totally understand that, that doesn't matter so much. This wasn't that hard to do. I just took the 2, 4, 3, and then the other vector was just the difference. Now I could have, when I did the ABC vector, you'll notice I subtracted 5 minus 2 and 7 minus 4 and 8 minus 3. I could have actually done that the other way. So I could have done 2 minus 5, 4 minus 7, and 3 minus 8. In other words, this ABC vector, I could have written it as negative 3, negative 3, negative 5. The only reason, I promise, the only reason I did it the way I did was to avoid extra negatives. But I just as well could have used negative 3, negative 3, negative 5, because after all, t could be negative 1. Right? So it would have just brought me right back to this anyway. T is allowed to be any number. Okay? Or for that matter, you can use 30, 30, 50. You know, that's what it'd be anyway if t was 10. Right? You understand what I'm saying? So this little vector here is sort of arbitrary. And that means many people could have different answers on your test. So I have to grade your work very carefully. You just need something that's like 3, 3, 5. It could be 6, 6, 10. It could be 30, 30, 50. It could be negative 300, negative 300, negative 500. Any multiple of this will work here. But this one here has to be one of the two original points. Either the 2, 4, 3 or the 5, 7, 8 has to go in the first point. Or if you happen to know other points on the line, you could put those in. So we get an infinite set of vectors that all point from x naught, y naught, z naught to all other points on that line. So there's a little bit of theory here that might be hard for you to grasp, but hopefully the mechanics wasn't too hard at all. Okay, now there happen to be two other ways at least where we can write our equation of the line. This is our answer. I've already boxed it, but let's play around with it and write it other different ways, okay? So one thing we can do with this part of the vector is we could distribute the t into here, okay? You're allowed to do that. So in other words, this would be an equally valid way to write it. X naught, y naught, z naught plus vector ta, tb, tc. Nothing wrong with distributing a scalar into a vector. Or, since you're adding these two vectors, you could just collapse it all into one vector, x plus ta, comma, y plus tb, comma, z plus tc. And since the left side, r of t, is really just its own vector, you could write this side as x, y, z. So I haven't really done anything new, but I kind of rewrote things a little bit. I distributed the t, collected the two vectors into one bracket, and labeled the left side, instead of r of t, I labeled it as x, y, z. Okay? And now, since these are two equal vectors, right? Since these two green vectors are equivalent, that means their components must be the same. So x is equal to x naught plus at, and y is then equal to y naught plus bt, and z is equal to c naught plus ct, you see. In other words, we can take this out of vector form and write those three things I just said, like this. Since this is x, y, and z, you can write x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. You might say, why would I want to do that? Well, these are parametric equations now, see? So this is the vector form of a line. This is the parametric form of the line. No big deal, it's just a different way of looking at it. But you know how questions are sometimes worded a little differently, right? So one question might give you vectors sort of at the beginning. Another question might give you a couple equations like this, you know. So you just need to be flexible and realize, oh, this can be put back into a vector if I wish. Okay? Okay, another thing we can do is we can isolate t in these three expressions. Right? Once you pick a value of t, that fixes your x, y, and z in space. Okay? For example, if you pick, you know, t equals 10, right? X has a particular value now, y has a particular value, and z has a particular value. And you just basically chose one of the points on the line. So when you say t equals 0, you have just chosen this initial point, x naught, y naught, z naught. When you choose t equals 1, you just jogged over us a little bit and picked a different point on the line. So you're basically choosing points on the line every time you choose a t value. Okay? So since the t value in all three of these equations is exactly the same, it might make sense to isolate t in the first equation, isolate t in the second equation, isolate t in the third equation, and then set all three resulting expressions equal. Okay, so this is going to give us our third and final form. So if you isolate t in the first equation, you get basically x minus x naught over a. If you isolate t in the second equation, you get y minus y naught over b. And you guessed it, the third equation yields z minus z naught over c. And since these are all exactly the same value of t, you can write x minus x naught equals y minus over a equals y minus y naught over b equals z minus z naught over c. A quick comment on this. If, for example, let's say that a or b or c happens to be 0, then just don't write that fraction. Okay? It's kind of like law of sines. You know, in law of sines, you have the three fractions, sine A over A equals sine B over B equals sine C over C. And you kind of cross multiply them and play around with them, right? This is sort of the same idea. Just know that sometimes A is 0, which means you're not really supposed to write this first fraction, because it will be undefined. But you can make a little note, you know, x doesn't exist, or whatever. Or, I'm sorry, t doesn't exist for the x equation. Or just leave it out. Just don't write it if A is 0, or B is 0, or C is 0. Okay, now what we're going to do is we're going to take our example 1 problem, which we worked hard to get our little vector. We're just going to convert it over to our other two forms, parametric and symmetric form. This is called symmetric form. Question before we do it?
Is it okay to think of A, B, and C as the change in X, the change in Y, and the change in Z over
Yes.
the interval of T?
They are kind of like
So would it be
delta
like,
x, delta y, and delta z.
would it be, I'm thinking of it like change in X over change in X equals change in Y over change in B for that equation right there. But I guess the X doesn't, you don't plug a value in for X. A, B, and C.
The only difference between A and x naught is that they are in a t to 1 ratio. So x minus x naught is the literal difference between the 2 points you chose.
Yeah.
A is just a component that points in that direction, that has the right x coordinate direction. So it's a little bit hard to draw this, but you could actually draw it all in 3D, and you could actually label A, B, and C in the picture. I'm trying to avoid getting too complicated, so just know that this is the third and final form of our equation of a line. So the first one was vector form. The second one was the parametric form. And after isolating t and setting these equal, this is called the symmetric form. They're all equally valid forms. It's kind of like, you know, y equals mx plus b, y minus y naught equals m times x minus x naught, and then maybe you know some others, you know, like maybe you know the polar form of a line or something. Okay? It's 3 different forms. Which means our last example, we should be able to just take that and convert it over to the other two forms. Okay? Zoom out a little bit so we can finish this lesson. So our example, our answer for example 1, which remember was x, y, it really was r of t R of t equals 2, 4, 3 plus t ABC, right? So 3, 3, 5. This answer can now be written as xyz equals 2, 4, 3 plus t, 3, 3, 5. In other words, x is 2 plus 3t, y is 4 plus 3t, and z is 3 plus 5t. If you isolate t in the first equation, oh, by the way, this is the parametric answer. They asked us for that. If you isolate t in the first equation, you get x minus 2 over 3. If you isolate t in the second equation, you get y minus 4 over 3. And in the third, you get z minus 3 over 5. In other words, you can write x minus 2 over 3 equals y minus 4 over 3 equals z minus 3 over 5. And this is your symmetric form. And one form is no better than the others, you know. Except I will say this, when you stare at the symmetric form, it may not speak to you as loudly as the vector form does, right? Once you understand the vector form, it kind of speaks the loudest. Like for most students, they're like, okay, I think I kind of understand that. It's kind of like a starting point, and then you're stretching the vector over to another point. And this is the direction you'll be traveling. Delta x is like 3, delta y is like 3, and delta z is like 5. That's your changes in x, y, and z. And the t just kind of stretches it to various lengths. Okay. So very much like b plus xm. But this one might not speak to you as loudly yet until you really, really, really think about it. But anyway, they're all valid forms. Okay, now, some questions could come up, right? For example, we haven't really talked about Y-intercept. Why is that? Well, because not all lines have a Y-intercept, right? Like if you look back at this picture I drew for you here, this green line is being formed by all the red points. That thing doesn't actually hit the y-axis, ever. The y-axis is actually down here. I'll label it for you because I never did. This was the x-axis. This is the y-axis right here, see? This line up here doesn't ever touch the y-axis, okay? If I'm looking at it right, it looks like it kind of passes between the z-axis and us, you know? And then it just kind of goes off into space. But one thing it probably does do is it probably does hit the desk. You know what I mean? It hits the desk. Like in this picture, remember the desk I drew, the IKEA desk? I'll bet that line hits the desk somewhere, right? And there are 3 planes that might be interesting to study. The desk itself, which is the xy plane. Let me draw that desk again. This is the xy plane, right? The flat desk. And then we also suspect that the line might hit this plane. You know, this is like the YZ plane. Or it's probably very likely that it also hits the XZ plane. A little bit hard to draw, but what I'm saying is there are sort of 3 planes. Wherever 2 axes meet, they form their own plane, right? So whether it's the x and y axes, which are perpendicular, or the y and z axes, which are perpendicular, or the x and z axes, which are perpendicular, they're going to form their own sheet. And I'll bet that line hits all 3. In fact, it would be kind of rare for it not to, don't you think? Okay, so we'd like to find those points of contact. Where does the line touch the xy plane, the desk? You know, where does it touch the yz plane? Where does it touch the xz plane? Okay, so this is actually really easy to do. When a line hits the xz plane, you would expect z to be 0. Okay? It's like being on the desk, you know, and that's where z is 0. It's flat. So setting z equal to 0 in the parametric equation, z equals, 3 plus 5t, basically gives us 0 equals 3 plus 5t, you see. So t is negative 3/5. Right? So there is a t, right, that would cause the line to actually touch the desk. Remember I told you when you pick a t, you're picking a point on the line? Well, if you pick t equals negative 3/5, you've chosen the point on the desk. Where is it? Well, you've got an equation for x, y, and z right here, parametric right there. You know t is negative 3/5. So we're going to find x, y, and z. Z will be 0. Okay, so x is going to be 2 plus 3 times negative 3/5, which ends up being basically, it's basically 10 minus 9 all over 5. So this is 1/5, is that right? I think I did that right. And y is the equation, 4 plus 3t. So 4 plus 3 times negative 3/5. So basically 20 minus 9, so 11/5 for that. And I guess I could calculate z again, but I know it's 0 because I was the one that set it equal to 0. So the point 1/5, 11/5, comma 0, is the magic point on the desk, you see, where the line passes through the desk. That's kind of practical. Question? This is 20/5, and you're subtracting 9/5, 11/5. Did I make a mistake? Is it wrong? Oh, okay. Similarly, we can also set x equal to 0 to find where it passes through the yz plane. And you can set, y equal to 0 to find where it passes through the xz plane. So I was saying, you've got this blue plane, this green plane, this red plane. The line probably touches all three of them. We've already found where it hits the blue plane. Let's go ahead and find where it hits the other two planes, Okay. Okay, so we're going to set x equal to 0 to get the point where it passes through the yz plane. We're going to set y equal to 0 to see where it passes through the xz plane, you see. So let's get busy. So if we set x equal to 0, we get 0 equals 2 plus 3t. So t is negative 2/3. So we know that x is 0. We just made that happen. We are going to use negative 2/3 and plug it into our y equation and our z equation. And I believe we got basically 12 minus 6. I think we get 2 for y, right? Because it's 4 minus 2. The 3's cancel. 4 minus 2, so that's just 2. And then 3 plus 5 times negative 2/3, that's basically 9 minus 10. Negative 1/3, I believe, for the z. So this is the magic point, you could say, where it crosses through this red plane, the zy plane. And then the last exercise for today is to find where it passes through the xz plane. So you would actually set y equal to 0. So if you set y equal to 0, you get 0 equals 4 plus 3t. Naturally, t then is negative 4/3. And that means that x is going to be 2 plus 3 times negative 4/3. In other words, 2 minus 4. And z is going to be 3 plus 5 times negative 4/3. Sorry for the sloppy handwriting. The edge of the screen the stylus doesn't work very well towards the edge of the screen. And this basically gives us 3 minus 20/3, or you could say 9/3 minus 20/3, negative 11/3. So I'll write my answer here. The x is negative 2, the y we chose to be 0, the z is negative 11/3. And this is the point where the line contacts the green plane. So without having to draw everything, we can totally visualize those intercept points. So they're not like axis intercepts, they're like plane intercepts. Does that make sense? And there's so much more we could do with a line, it's ridiculous, but let's not. Okay? So I just want this to be kind of something you can use. If you're in Calc 3, the very first day, the professor's going to write this on the board. He's going to write, this is equation of a line, deal with it. And I want you to see my interpretation of it. It's like, okay, you got a point, you're stretching a vector over to another point, and you're making it as long or short as you want to collect all the points. Okay? And that's real loosey-goosey, but that's the gist of it. That's all you really need to understand, right? Okay, so that's the end of that one.